Hi there, folks. Today we're looking at ratios and proportions, and you might remember some of this. We're going to take it a step further and talk about extended ratios and that kind of stuff. But a ratio is just a comparison of two quantities by division. All right, we essentially set up a fraction that is a ratio. All right. For example, if I look at something like this guy, it says the Washington Monument is 555 feet tall. A replica of the monument, so a little scale model, is 18 inches tall. What is the ratio of the replica to the full-size monument? And so there's a couple ways we can kind of approach this. If I just take it as it's written and say, hey, let's write a ratio, I could say, and when we look at this, it says replica to the full-size model. That's important because when we talk about that ratio in that order, we want to express it in that order in our fraction as well. So replica to the full-size model would be 18, and we can write a ratio this way to 555. And I would have to reduce that. So even though it's in this format, I still have to reduce it just like I would with a fraction. And each of those is divisible by 3. So I can reduce this to 6 and a 185. And because the units are different here, I do have to include them. That's 6 inches to 185 feet. Okay, so that's the kind of the conversion between the replica and the full-size monument, okay? So that's one option. We could do the same thing as a fraction and say, hey, that's 18 over 555. And we get the same thing. It's 6 inches compared to 185 feet, okay? So those are first two options. The other thing we might look at is we might look at this and say, hey, I want a straight scale factor in terms of this thing. I want a straight ratio that doesn't have different units. And if you do that, what we'd have to do is we'd have to convert one of these guys. And so there's two ways you could do this. You could say 18 inches is 1.5 feet. Or you can convert the feet to inches by multiplying it by 12. I could leave this as 18, and then this would be 6,660 inches, okay? And really, what's nice about this, no matter which of these units I go to, each of these is going to reduce to the same thing, okay? And so if I reduce each of these, I get 1 to 370. Here I also get 1 to 370. I could also express that as a fraction, 1 over 370, okay? So I get the same thing each time. But that's if I was comparing inches to inches, all right? And what's nice about that in terms of that kind of ratio, that's a straight ratio when we look at that. That first guy is actually a special kind of ratio because it's two different units, okay? So convert them, bring them to the same unit and write your ratio. We could consider that then a scale factor, which is really nice. Or we can write the ratio in terms of two separate units. Then it's a rate, and that would allow us to convert back and forth, okay? If I look at something like this guy, it says a fundraiser is selling milk chocolate and dark chocolate candy bars. The ratio of dark chocolate to milk chocolate is 3 to 5. If the plan is to sell 240 candy bars, how many of each are needed? And so if I kind of look at this, again, I have to think about the units. So like if I were to write this ratio as a fraction, that's dark chocolate. Reading is hard. To 5 milk chocolate. That would be an acceptable ratio for this thing in terms of comparing these guys, okay? But then if I wanted to know, if we plan on selling 240 candy bars, how many of each are needed? If you think back to your days in algebra, one of the things about setting up a proportion is making sure the units match. And so if I looked at something like this, if I wanted this to be dark chocolate over milk chocolate, well, it has to equal dark chocolate over milk chocolate when I set up the second fraction. And when you look at that 240, that 240 is not dark chocolate or milk chocolate. That's the total, all right? And so the really important thing here is that as soon as I have this ratio, it actually gives me two more ratios, okay? See, that's the dark chocolate to milk chocolate. So that would be 3 dark chocolate. Let's compare that to the total. If it's 3 parts dark chocolate and 5 parts milk chocolate, that's a total of 8 total candy bars. And I'm going to put a T for total. I could also compare the milk chocolate, say 5 milk chocolate to the total would be 8 over T. And so we automatically have these ratios. If I have the ratio of two things being compared, I automatically have the ratio for the total as well. Okay, so I have that. And when I look at something like this, that's the ratio that I need, because that's what I'm given here. So if I look at something like this guy, I can say, hey, it's 3 dark chocolate to 8 total candy bars. Now when I write this, I don't know how many dark chocolate, but I know how many total candy bars is 240. Okay? And so let me get rid of these guys. Those aren't actual variables. That was just me labeling. Let me get rid of the labels. I used D as an actual variable. Now you can solve this by cross-multiplying. Okay? And so if you multiply this, if you can cross-multiply here, you get 8D equals. That's going to be a 7,200. 720. Oh my. 720, and now you have to divide each side. And when you do that, you get a D equals a 90. And then from there, we don't have to do any more ratios. We can go right to this thing and say, hey, you know what? That's going to be, if that's 90, to get to that 240, the milk chocolate has to be a 150. Okay? The other thing you can do is as soon as you have this guy, something like this, because I'm comparing the same units, because it's a scale factor, I'd say, hey, that's 3/8. So 3/8 of the total candy bars are dark chocolates. Watch this. Multiply that by the 240, and guess what? There it is, 90. Okay? And so that's another way to do it. I could do the same thing with the other piece. I could say, hey, 5/8 of these, 5 out of the 8, give me milk chocolates, so 5/8 of 240 automatically gives me the 250, okay? It's not always best to set up a proportion when you're given ratios. Sometimes ratios can be used as scale factors, which means I can multiply to get these answers, okay? That was the dark chocolates and that was the milk chocolates. Let's talk about an extended ratio. An extended ratio is when I have 3 pieces being compared or more. And we don't typically, we're not going to write this as a fraction, because then I'd have a fraction within a fraction, and then we have a mess on our hands. So we kind of keep these in this format of comparison using those colons, okay? So A to B to C. And I could have more values if that was compared to a 4th value. I could say A to B to C to D. And we use this a lot in geometry because we have a lot of kind of things that are set in terms of 3s or 4s. Like if I'm talking about the angles of a triangle, those are always set in terms of there's 3 angles, okay? And if those 3 angles appear in a certain ratio, I would use an extended ratio to express those, okay? If I looked at the angles of something like a kite, I could express those in extended ratio using 4 values, okay? If I look at something like this guy, it says the lengths of the sides of a triangle are in the ratio 3 to 5 to 6. If the perimeter is 98 inches, find the lengths of each side. And so because we have 3 sides of the triangle, it makes sense to express it as an extended ratio because I have 3 pieces. And what's nice about this, if we kind of think about this from the perspective of a scale factor, okay, I could easily just look at this and say, hey, this is 3 of the parts, this is 5 of the parts, and this is 6 of the parts. And maybe I should have labeled that differently so it's, since this side does look a little bit longer, yeah, might as well. But then if those represent a scale factor, it means that each of these actual sides would just get multiplied by that thing to give me the length of the actual side. And so as soon as I have these in series like this, I could just write it like this and represent it as, hey, 3 times something, 5 times something, and 6 times something, okay? Because if they're in those ratios, think about the idea of reducing a ratio. It's really just dividing. So to get back to the actual side lengths, it's just multiplying each of those by the same thing. And so I can express it this way. Then it says if the perimeter is 98, well, that can allow me to work backwards if I add all these up and find out what the length of each side actually is. Find out what that multiplier should be, what that x value should be. And so as I simplify this thing, let's see, that's going to give me a 14x. And then, of course, I can divide each side by that 14, which gives me a 7. And so it didn't ask me for x. It didn't ask me what am I multiplying by. It asked me what's the length of each side, which means this side up here is a 35, this side is a 21, and this side is a 42. And one nice thing about this is I can easily check this by rewriting it as a ratio, 21 to 35 to 42. Let's write it as an extended ratio. If I reduce that ratio, they're each divisible by, of course, 7, and it would bring me back to this guy, okay? But again, that's why we can express it this way just in terms of multiplication. Say, hey, if that's the ratio, I could multiply all three of those by something and get three sides that fit into that ratio, okay? When we talk about proportions, we already know how to solve proportions, but just a reminder, when we have proportions, we can solve by cross-multiplying. That's kind of the one we knew. But then we can also solve this by using extremes and means. So when it's in that format of using the colons to express our ratios, we can just multiply the outside numbers, and that equals multiplying the inside numbers, okay? That's what we mean by the extremes and the means. That's how we label these. So the outside numbers are the extremes, the inside numbers are the means. So if I wanted to solve this, I would just do extremes. When I multiply the extremes, I get AD. When I multiply the means, I get BC, okay? And it's the same thing that I get if I cross-multiply over here. If I cross-multiply, I get AD equals BC. Again, cross-multiplying is the one that we know, the one that we're familiar with, okay? And the fact of the matter is you could always rewrite this guy as A over B and rewrite this guy as C over D and then cross-multiply and you get the same thing, okay? But if we talk about extremes and means, we're referring to kind of the same thing that we do when we cross-multiply, okay? For example, if we look at something like this guy, I'm just going to cross-multiply to solve this thing. Again, we should already know how to do this, but 5 times the x gives me a 5x. Equals 6 times the 4 gives me a 24. And yeah, those are equal to one another. One of the mistakes that students make is we kind of get in ratio mode, and we multiply those things, and we get the 5x and the 24, and we write things like 5x over 24 or something like that. No, when you cross-multiply, the multiplications are equal to one another, okay? So now I divide each side by that 5, and I get a 4.8, okay? The next one I cross-multiply here, y times 9 is a 9y. Here, y plus 4 times 3, I have to multiply that entire thing by the 3, which is my distributive property. So that's a 3y plus 12. And if you need to write an extra step there of 3 times y plus 4, that's fine. But again, we're multiplying that entire thing, so that's our distributive property. And now I would subtract that 3y from each side. I would divide each side by the 6 and get y equals a 2. Okay? And then if I look at the last one, if you're not comfortable with this, if you're not comfortable with extremes and means and that kind of thing, we could just say, hey, you know what? Let's rewrite this as a fraction. You could write that first one as 15 over m plus 1, and then write the second one as 3 over m, and then cross-multiply. But same thing, I could just do extremes and means. Here's the extremes, 15 and m. When I multiply those, I get 15m. Here's the means, the middle guys. When I multiply those, again, I have to multiply that entire thing by 3. That's my distributive property. That's a 3m plus 3. And now let's solve this thing. Now I subtract the 3m from each side. And I divide each side by 12. So I get a 1/4 or a 0.25. Okay? Let's talk about properties of proportions. Properties of proportions are some of these things that we can do when we have proportions. There's ways that we can rewrite it. There's things that we can apply to make this a little bit easier. And we've kind of gone through some of these already, and you've probably seen some of these already. But the first one is probably the most obvious, and that's that you could flip each of those fractions. But if you flip one, you have to flip the other. So if I were to flip this first fraction and make it b over a, well, I have to flip the second one and make it d over c. Okay, so that's one of the things we can do with proportions, and they'll still be equivalent. All right. If I look at the next one, I think this is the most underrated and underutilized property, and that's that I can switch the diagonals. So like right here, you see this c and this b? Those can trade places, and the proportion is still correct. It's still equivalent. Notice here, the c is now here, and the b is now up here. okay? I can switch diagonals anytime I want with proportions, and it is the same thing. Let me use a quick example. If I have something like this, 1/2 equals, 4 over 8, okay? We all know that that is the same thing, right? But watch this. Switch the diagonals. Switch like the 4 and the 2. Now I have 1 over 4 equals 2 over 8. And the question is, before the 1/2 is the same thing as 4 over 8. They're both 1/2. Is this the same thing? Well, of course it is. 1/4 equals 2 over 8. That's still 1/4, okay? You can always switch one pair of those diagonals. You can always switch a pair of diagonals, and you will still have an equivalent proportion, okay? The next one, we're allowed to do a little bit of addition as long as we add the denominator to each of those numerators. So like here, this guy right here, I can add this to the numerator as long as I do the same thing with the other fraction. I add that to the numerator, okay? This one doesn't come up a lot. It doesn't happen super often, but we kind of used that same thing when we were talking about the proportion with the chocolates, and that idea that we have more than just the proportion or just the ratio that was given. We have some of these other ratios in terms of the totals and that kind of thing, okay? For example, if I look at something like this guy, I'm given that x over 6 equals y over 7. I want to kind of complete the proportion here. And so I have to think about what happens. So right here, right now I have x over y. So instead of x over 6, I have a y here in its place. So think about what I would have to do that. I would have to switch these, okay? And so if I switched those diagonals, this second fraction would be 6 over 7, all right? And if x over 6 equals y over 7, then x over y has to equal 6 over 7, okay? If I look at something like this guy, I've got d over 5 equals r over 10, and now all of a sudden I have 10 over r, and so when you think about it, that looks kind of like this guy, except instead of r over 10, it's 10 over r. I flipped it, which means I have to flip the other one, 5 over d. These are the properties of proportions, okay? So I can still have an equivalent proportion here, all right?